Ladies and gentlemen, good morning. I'm Ebothe of France. Since the beginning of my talk, I would like to invite you to retain one main word of my talk. It is properties, to restrict to the physical one of material thin films. I believe that our usual idea of that notion should be revised right now because of many reasons you will discover through my talk. For that, I will propose a particular approach of this idea, but to make this approach interesting in science, it should be validated by a concrete experimental illustration. Nickel thin films announced here will serve for that. Manifestation of a material thin films in properties is the result of interaction between the films and the physical field that can be electrical, magnetic, or electromagnetic one. And for doing science, we need to quantify that property. That means to give a value to that property. Exact value are always researched. This is the dream of any researcher. For reaching our objective, there are two ways: technical measurement in one side and theoretical calculation in another side. Because of time, I will just focus my mind to the technical measurement. Suppose you have one technique. You can measure the film property of one sample. The same sample, you can use it to do the same measurement if you have another equivalent techniques. Rarely we will have the two value obtained exactly the same. That means that there are always something like an approximation of in your result, in your measurement, in your value. This is confirmed sometimes by the constructor of the setup. In general, they provide uncertainties in your measurement. These uncertainties are linked to the techniques you use. I can call them instrumental uncertainties. I will draw your attention now to another kind of uncertainties whose origin is the morphological aspect of your sample. These uncertainties are directly linked to the sample itself, and they appear whatever the technical measurement used. And I will just try to make it evident through a particular approach called geometrical approach of thin films. The departure point of this approach is a perfect thin films. A perfect thin film is, of course, a mathematical representation only. These representations show that the surface of your samples has no irregularity. That means the corresponding surface roughness is equal to 0. The material, the bulk, is homogeneous and regularly homogeneous, and it is characterized by the thickness of the samples. And thickness and D, because one is horizontal and another vertical, both are called geometrical characteristics. But here, because of the perfection, D and sigma are exact value. Let's go now to real material thin films obtained from deposition conditions, whatever the deposition process, whatever the conditions used. In that case, the film surface always have surface irregularity at different level, of course. In that case, one important point, the surface roughness represented by sigma and the thickness D of the films are unavoidable first. Secondly, they are inseparable because both of them are induced by the same deposition process and conditions. Here, D and sigma have mean values only. They are the indication of the film morphology. And now, generally, when we are dealing with a real material thin films, the tendency, the trend, is of course to make it more perfect, as close as possible to the perfect film. That means we applied a etching treatment. But everybody knows that etching treatment is removal of a part of the material, you know. In that case, the etching treatment is practical only for thick samples. When you are dealing with the nanofilms or nanostructure samples, it is very dangerous, sometimes tricky, because sometimes also is impossible, because you might remove all your material and then you won't lose, you will continue doing science. This is the first point. The second point is the initial state of your sample is not uniform. That means locally at the surface there are several points. The points are not equivalent. If you do, for instance, a chemical treatment, you will attack, but at the end of your treatment you cannot expect having a perfect flatness. That means you will just do a smoothing, but the smoothed or the initial samples, both of them are characterized by geometrical characteristic. That means D are different to sigma, are different to 0, sigma are different to 0, always. If you try to have the measurement of your property, that will be the result of the combined effect of D and sigma. This is not sufficiently underlined in the physics of material thin films. For doing science in general, if you want to study the evolution of film properties, the more practice, in practice, you know, we used to use a series of specimens, but discriminated specimens. There are, I can say, two options to discriminate the specimen of your series: by gross process, as proposed here, or by deposition time. Whatever selected option, if you vary the different samples by having a variable in your deposition process, you will always have different value of the couple, D1, sigma 1, etc., different to, etc., etc. Always a couple, because you cannot separate D and sigma. You cannot see the evolution of D or the evolution in a separate way. No, they are connected. In general, the difference between the D values are more noticeable. However, the evolution or anticipating the evolution of sigma values are sometimes very difficult. So, if you have the presence of the two geometrical characteristics, it's very difficult to study the property of your evolution, the property of your samples in a simple way. So, you should be rational, and for being rational, there is another step. That step is to study the relationship between sigma and D. In that case, you have three situations. When the ratio between the thickness to sigma, thickness to surface roughness is superior or equal to 10 to 2, that means that you have a sigma which is largely inferior to D. In that case, approximation is possible between the two characteristics. In that case, you can see that D is the main contributing characteristic, geometrical characteristic of the films, and then you can use D to sort your samples. And after sorting your samples, you can study the evolution of the property by the expression P versus D, which is commonly encountered in the literature, but sometimes people use it without any precaution. The second situation is, I can say, for intellectual satisfaction. And this is not really suitable for the measurement of physical property, because we have sigma and d the same value. Experimentally, it's very difficult to reach that objective. So I will forget it and go directly to the third situation. Third situation is the ratio is inferior to 10 to 2. That means the value of d and sigma are very close. In that case, approximation is impossible. No? This is the case. Generally, it's not so rare as we can imagine, because you can find this with nanofilms and nanostructure samples. In that case, both characteristics are simultaneously contributing geometrical characteristics. So, how to find the solution in that case? In that case, I think that combining the two characteristics, that means maintaining the ratio and giving a particular, can I say, identity to that ratio, as I'm presenting here, I give the identity tau. I give, I resemble, gather the two, can I say, characteristic through a third geometrical characteristic called tau. This is unusual. I didn't find that way of doing in the literature. But I think that tau is very relevant and adapted in that situations, so that you can study the evolution of your film properties using the expression P versus tau. This is in a better agreement with the film reality. Partial conclusion. D is adapted for thick films and tau for mesoscopic scale thick samples. Tau and D have a similar role for the study of the same material physical property, but P versus D can never be directly compared to P versus tau, because they are different situations. Let's go to a concrete analysis, concrete result. I told that I use nickel thin films. Nickel thin films are here prepared by electrochemical process. Electrochemical process for which the film are obtained by using the cathodic voltammetry cycles, for which the main variable is the scan rate of the cycle. The value of the limit selected are here presented, and from them the discrimination of the sample are then obtained by deposition time options. The film are characterized as here: thickness by cross-section scanning electronic microscope images, and the topography, that means the roughness measurement by IFM, and global property by VSM magnetometer, and local magnetic property by magnetic force microscope, MFM. Here is the result of the topography obtained from two samples obtained from the extreme value of the scan rate. Higher scan rate here give bigger grains, smaller scan rate, smaller grain, but the two samples have globally the same morphology. The result obtained with all the investigated samples are given here. You can see that we can order the samples, investigated samples, using D value and tau, and here we have the same evolution with same evolution of the samples. The order is the same using D or using tau. This is a coincidence, because it's not always obligatory to have the same evolution. Here, the link between the different geometrical characteristics, decrease and increase of each one of them versus film thickness. But before studying the property of the films, and it's better to examine the approximation possibility. The condition is given here, tau superior or equal to superior to 100. Applied to our Nike samples, you can see that the two limits in the value of tau lead both of them to the impossible approximation. That means that in our case, sigma cannot be neglected compared to d for all of our samples. That means that you cannot study the evolution of the film property using d variable. You should, of course, use tau variable, or the y p versus tau approach is here fully eligible. Application to the magnetic property of the films, we can see here difference in the tilting of the hysteresis slope of the sample of the two samples selected. This is an indication of magnetic anisotropy, and also this shows that tau value affect the global magnetic property. That means saturation magnetization, remanence magnetization, and magnetic creasivity. Let's follow the effect of tau. With the squareness of the samples, we see that there is an evolution toward the evolution of the squareness upper to superior to 0.5. And this is something like, can I say, the similarity, demonstration of the similarity of the behavior of tau and d. And if you accept that similarity, we can say that we have here an indication of a magnetic reversal of the samples that are ruled by the domain wall nucleation and motion process. Okay, let's see the evolution of creasivity. In red here, expression in red here correspond to the result obtained, the profile of the curve, and we can observe that the profile of the curve is very close, respect the Néel prediction law when we use d instead of tau. This is the first confirmation that tau and d are similar in their role. Here, more important is the magnetic phase image given here that will allow to do determination of the local magnetic properties. An example of local magnetic property is here, magnetic domain size. We can follow here the evolution of this property versus tau. In red is the expression corresponding to the result, which is here exactly similar to the result of the Kittel prediction law, when d is used at the place of tau, which is the second confirmation of the similar role of both characteristics. In conclusion, I can say that I hope that this work will convince you to take care when you are studying the property of the sample, thin films. Take care, particularly when you are dealing with nanofilms and nanostructure samples, because tau and d are different parameters that you cannot mix them. Okay. For the perspective, I think that it is good to try to continue this work with the studying of other ferromagnetic material, and also to continue by studying the evolution of other film properties. One word to the funding support. Thank you very much for your attention.